So let's solve this problem now. Let's take a look at this example. So I've got actinium 227, and then we know that the atomic number is 89, mass number 227, in the case into thorium 227. So we just by this first sentence we can observe that it has decayed into another element. The mass number is still the same, and the proton number has changed, and we can see that it has increased. So what is the kind of radioactive decay that I could have to turn this actinium into thorium? So what do I need to get my proton number to increase? Well, I will need a neutron. One of the neutrons in the nuclei of this actinium, it's going to split. It's going to split into a proton, which basically conserves the mass. It's roughly the same mass. However, don't we have to conserve the charge as well? So we will need an electron. So proton, electron, and as we are going to cover in a few topics, our antineutrino. So this is beta minus decay. So since this is beta minus, we could just add the electron here. So electron mass 0, charge -1, and our antineutrino. And if we check, 89 is 90 minus 1 plus 0, and 227 is 227 plus 0 plus 0. So, check. That's the first decay that's happening here. Now let's continue. Thorium-227, which is the daughter, one of the daughters here, has a half-life of 18 days and undergoes alpha decay to the nuclide radium-223. So first, we've got N0 of thorium is 18 days. That's our half-life for thorium 227. Usually we give the name thorium-227 because, well, when we say thorium, we know that it's the atomic number is 90, otherwise it wouldn't be thorium. However, since we have different isotopes in nature, we might have different numbers of mass. So when we specify thorium-227, we are making sure that we're specifically talking about this isotope in which the mass number is 227. If we just say thorium, it would be ambiguous. We wouldn't know what kind of thorium are you talking about. Well, now this thorium then, which is one of the daughters from our first beta minus decay, is going to undergo an alpha decay to nuclide radium-223. So let's also write this equation. So we would have thorium 227 and 90, and it's alpha decay. So we're going to have a helium atom, okay? Usually I just put alpha, right? And mass number is 4, atomic number is 2, plus radium 223. This is given, and this we can work out. If we need to add to get 90, this would be 88. And if you look at the periodic table, it should work. So this is what you use when you're using your half-life to calculate how this radioactive decay is going to decrease, this rate is going to decrease over time. If you have, let's say, half of the original particles, the original radioactive particles, this count rate should drop by half. If we knew the background radiation, we would have to subtract here our background radiation, because then we would know exactly how much of that radiation is only regards the elements that we're talking about. Okay. So letter A, define the terms nuclide and half-life. So nuclide, well, it's a nucleus with a particular number of protons and neutrons. It's different than an element. So for example, when we talk about thorium-227, that is a nuclide because we're specifying how many protons and how many neutrons. If we just mention an element on the periodic table, as I've told you before, if you look for the number of mass, it's going, most of them are not whole numbers. They are broken numbers, decimals. So you can see some points, something here, and that's because in nature you have lots of isotopes. So when you do the average, your mass number will not be an exact number. However, when you're talking about a nuclide, you're talking about a specific isotope of that, a specific particular isotope of that substance. So in this case, it's not any thorium, it's specifically thorium with 227 mass number. And then there's no ambiguity here. Now, what is half-life? Well, half-life is the time for the count rate to halve, right? Or the time for half of the number of nuclei to decay into nuclei of another element. That's what half-life is. So when half of those, for example here, actinium, when half of those become thorium, you've reached one half-life. When half of those thorium become a radium, you have reached the half-life. And those half-lives, they're most likely different. So, done. Letter B, copy and complete the following reaction. So it's our first reaction here. It's a beta minus decay, and that's fair enough, right? We've got thorium, we discussed this before. Done. Letter C, draw a graph to show the variation with time t from t equals 0 to t equals 72 days of the number of nuclei in a sample of thorium-227. So what we have to do here, we have to basically analyze those days in terms of half-life. So we are told that the half-life is 18 days, which, fair enough, is 1/4, 1/4 of this, isn't it? Anyway, so let's analyze this. Let's say that I've got N0 here, right? That's my initial count in this case. I'll not put the numbers in yet. After one half-life, this would be N0 over 2. After another half-life, this would be N0 over 4. After another half-life, this would be N0 over 1 over 8. Now, if this is 18 days, here it would be 36, right? 18, here it would be another 18, but overall it would be 36. Here it would be another 18, but overall you would have 36 plus 18, 54. And then if you wait another 18 days, the total number of days would be 72, wouldn't it? So we can rewrite this equation in this way. So the number of counts or particles is going to be the initial counts or number of particles times a half, which is your half-life, times the number of half-lives that you have passed. Now, in this case, how many half-lives have passed? You have to divide the 72 days by the 18 days, which is your half-life. So this would be 4. N0 in this case is the number of counts. So we have 32 counts, a half, and our exponent, a half, and our exponent would be 4, which should give us exactly the same thing as we have done just by thinking about it. So since the question is asking us to plot a graph, I will sketch one here, and you don't have to worry very much because there is usually some tolerance. They will accept some margin of error in graphs like this one in your exams, right? But try to make them as the best as you can. So let's add some scale here, 5, 10, 15, 20, 30, 35. So each slit here okay, so this is the number of counts, and this is time. Could be days, could be, well, let's put it in days. Okay, now my initial count rate is 32, so it would be somewhere around there. Okay, around here. My initial point is 32, and then what happens is that after one half-life it drops to half, so it will drop to 16. So let's say this is one half-life, so 18 days. It would be 36, 54, and 72. So this was 32, and then it's going to drop to 16. Then it drops to half again, 16. It's going to drop to 8. And then it will drop to 4. And then finally it's going to drop to about 2. And we should be able to pretend that it's a nice line. Okay, so those are our points. And there you go, that's a drawing a graph to show the variation with time t. Now determine from your graph the count rate of thorium after 30 days. So they're asking us, just by looking at the graph, right, and trying to find here what would be the activity at that point. If you were able to calculate, if they asked you to calculate, I'll show you. But here it's graphical, so you would have to find here about where it would be, and then you just find the point and find the height, and then again there is some tolerance here. They will probably accept some range of values, because here you can go a bit to the left, a bit to the right. It's not a problem, and your graph might be a bit, you know, tilted as well. Just try to make it as best as you can, so your answer here will be roughly what they expect. If we were asked to calculate, we could use exactly this same rule here. So n0 half over n. But in this case, what's our n going to be? Our n is going to be different. It's not 4 anymore, because we're not going through 4 half-lives. Now we're going through 30 over 18 half-lives. So 30 over 18, which would give you approximately 10.08 days. So 10 up to even to two significant figures is fine. Now the last part, so this is done, this is done. Now I'll outline the experimental procedure to measure the count rate of thorium-227. So you would not be expected to give a lot of detail, but there are a few things which are important. I'll put them written here, and I'll also read that for you guys. So here you are. You would use a Geiger counter right, or a Geiger-Müller tube as a detector, then you would have to measure how much radiation is being emitted, or how many counts. In this case, how do you measure it? By counts per second, or how many counts per some amount of time. And you do that several times, at least 3 times, to avoid any errors that you might get from sources of different radiations, or some awkward moments in which there's some solar flares or anything like that. So you try to avoid those by making several measurements, and then you make an average and divide by 100 to give counts per second, right? In this case 100, because you would measure for 100. But if you measure for a different amount of time, then you just divide by that time to get an average per second. So if you measure for a whole minute, let's say, you would divide by 60 seconds. So you do that in order to measure what is the background radiation. Right? So you do that, you measure your background radiation, and then you will subtract that from your measurements afterwards. So after you've measured your background radiation, you go to the actual thing that you're trying to detect, and then you can measure that and subtract what you've measured before. It's just like when in mechanics, you're trying to work your forces, and then you try to neglect the acceleration of gravity by making another frame of reference in which the acceleration of gravity is, your frame of reference is accelerating with with gravity, right? The same acceleration, so you can neglect that. That's how the planes that do that thing that looks to be 0 g, zero gravity, that's how they do that. They fall with the same acceleration as the Earth, and there you don't, as your frame of reference is also accelerating with the same acceleration as of the Earth, you don't feel it. That's how the space station works as well. Well, at the end then, you would correct your count rate by subtracting the background radiation. So those would be the procedures for you to get a proper value, and not to have anything that shouldn't be considered, like radiations from other sources as well. And that's done.